Okay, so hi everybody. So for the last section of this course, we're going to be talking about relativity and quantum mechanics. And the main goal I have here is to just introduce you to some of the basic concepts between some of these more maybe exotic areas of physics. I'm not going to be asking you to do lots of calculations. I'm mostly here to get you a sense of some of the counterintuitive results that come from these particular fields of what's typically called modern physics. So up through this part of the course, we've been talking basically about electromagnetism. We talked a lot about electric forces, we talked about magnetic forces, we talked about electromagnetic waves. And this is a topic shift, but it's a motivated one. The thing is, both of these pillars of modern physics, special relativity and quantum mechanics, did in fact emerge from people trying to make sense of the properties of electromagnetic waves. And as people started to look at these electromagnetic waves in more and more detail, they started to find issues with how they behaved. And this led, on the one hand, to the development of special relativity, and on the other hand, to the development of quantum mechanics. And again, so these are the topics I want to focus on this last couple weeks of the class. For this particular video, I want to focus on special relativity. Now, relativity is, of course, one of Einstein's greatest achievements, and was one of the things that led to a revolution of the understanding of how physical systems worked over 100 years ago. And what it emerged from was trying to understand how electromagnetic waves worked. As we talked about before, electromagnetic waves are freely propagating disturbances in electric and magnetic fields, and they form light, infrared radiation, radio waves, etc. One aspect of these waves that I emphasized is that these disturbances propagate at a very particular speed. The speed, which is denoted with the letter c, and is basically derivable from the fundamental constants in the definitions of the electric and magnetic fields. It is a very high speed. It's 299 million meters per second. What is key about it, though, is it just depends on fundamental constants of nature. This expression for the speed of the wave does not care about the source of the wave. It doesn't care about how it's being perceived or anything else. It is a speed at which light travels. And if you think about this a bit, it starts to create problems. Because it means that the speed of light seems to be independent of things. And that shouldn't be the case. Because normally we regard speeds or velocities as very relative concepts. For example, just to give a cartoon example, we can throw a ball across a room. The ball will move at some speed, call it v ball. A person could be running right alongside that ball at another speed, vp. If this person looks at that ball, how fast does the ball appear to be moving? Well, it moves from this person's perspective, basically at a frame where they're at rest, the ball is moving at a lower speed. If this person's running by fairly slowly, the ball is still moving fast. If this guy can run as fast as the ball is moving, the ball won't appear to move. And if he gets running really fast, he could go faster than the ball does. This is all kind of just intuitively how velocities and speeds are supposed to work. If this is correct, and this is really deep in electromagnetic theory, then that's not how light works. Light works in a very different way. I can shine a light in one direction and have someone running along beside the light beam. From my perspective, this light moves at a speed c. If those formulas are correct, then from the person who's moving's perspective, looks at this light and also sees it going by at the speed c. This guy can run as fast as he likes. And from his perspective, that light beam stays going at the same speed. That is very strange and sounds wrong. And in fact, a lot of people thought it was wrong, that we're missing something here. There's basically two ways out of this problem. One is that statement that the speed of light just depends on fundamental constants of nature and nothing else is wrong. That if I shine a flashlight and measure how fast it takes the light to travel, and this person who's moving really fast measures the speed at which the light travels, we'll actually disagree. One of us gets a different number than the other. That is not in electromagnetic theory. It would imply that there is an issue with the modern theory of electromagnetism. It's wrong, or at least incomplete. That's one option. And that was the option most people followed for a while. It was like, clearly this doesn't happen, so there must be something else going on. Electromagnetic waves are probably propagating through a medium of some form. Those equations that describe the speed are only in a particular reference frame where that medium doesn't move. This was an idea a lot of people had, and there was a lot of work done to try and measure variations in the speed of light. I am not a historian of physics. I'm not going to get into all the details. They never saw any. And nowadays, we still haven't seen any. The other possibility is that this is correct. This is actually what happens. But if that's what happens, it turns out that that has implications for pretty much all of classical mechanics. Our understanding of positions, velocities, accelerations, etc., all need to be adjusted. Now, this turned out to be the right option. And there were a few different people working on this particular idea, but the one whose name is most associated with it and the one who brought it all together and made it all make sense was Einstein. Einstein came up with the idea that light actually did this, and we just have to figure out what this means. This is one of the things that's really cool about this. Special relativity is something that gets treated a lot like an exotic area of physics, but in some sense, it's the most approachable. Whereas when I talk to you about Coulomb's law or Ampere's law, at some level, those were all developed empirically. That's how the world works. When we talk about special relativity, on the other hand, what we have are actually a set of postulates. We're going to just assume a couple of things are true and follow through the consequences of those. And those consequences lead to observable phenomena that are in fact observed. So rather than say, like, you've got to memorize a bunch of formulas to understand special relativity, that's not really the case. What you have to do are understand the two basic principles behind special relativity, the two fundamental assumptions, and see what those assumptions imply. The two assumptions behind relativity, and these are assumptions, but they appear to be correct, can be expressed as follows. First of all, The laws of physics are the same in all inertial reference frames. The second rule, the speed of light is the same in all inertial reference frames and is independent of the motion of the source or the receiver. This second one is basically what we were previously talking about. That for any observer, the speed of light is the same. We're just going to assume that. It's a weird thing to assume, but we can assume it. But we're being a little more specific about this. We're saying it's the same in all inertia. We're also saying something is special about something called an inertial reference frame. And that's an important concept. What is an inertial reference frame? An inertial reference frame is just a coordinate system, a frame of reference where Newton's laws of motion work. That is, objects at rest tend to stay at rest. Objects in motion tend to stay in motion. Objects in motion tend to move in straight lines at constant speed. Objects only accelerate if they have another object interacting with them. Those basic rules. If those rules hold, you're in an inertial reference frame. Now, you on Earth are not in an inertial reference frame because we have the gravity of the Earth pulling down on us all the time. So this is not something that's always easy to see. If you look at the motion of objects on a surface with no friction, that's a pretty good approximation of an inertial reference frame. But it is something we can at least imagine existing. And if you're out in deep space, again, it's a pretty good approximation. So if you have any reference frame where an isolated object like this cube is just drifting by at a constant speed, that's an inertial reference frame because that box has no forces on it, it has no acceleration, and it's observed to have no acceleration. Yay. This is an inertial reference frame where this box is moving at a steady rate. Another inertial reference frame is the reference frame of the box. If we were sitting on the box, from our perspective, the box doesn't move. The observer watching the box move by seems to drift by, but from the perspective of this person, the box doesn't move. It's at rest. That's okay. There's no force on it, so it should be at rest. This is also an inertial reference frame. So I can basically change the velocity of every object as long as I just change it by a fixed amount, and I can go from one inertial reference frame to another inertial reference frame. There is an inertial reference frame where this object is moving to the left at a constant speed. There's another one where it's moving to the right at constant speed. It could be moving up at constant speed. Those are all valid perspectives. And what's important to understand is there is no experiment you can do that would allow you to favor one over the other. That's what this first postulate is saying. That if in one reference frame this box is moving at a constant speed, and there's another frame where it's at rest, there's no experiment you could do that would say absolutely that one of these perspectives is better than the other. For example, if we were inside the box and had no windows or other things, there is no experiment we could do to distinguish whether the box is moving at a constant speed or staying still. And if you first of all think about, of course I could tell if something's moving. In fact, that's really actually kind of hard. You think like when you're in a car, you know you're moving. Well, yes, but it's not the fact that you're moving at a constant speed that you feel. You feel all the accelerations from the fact you're going over terrain or your car is turning, etc. if you're going at a constant speed and you do all of the equations of motion for kinematics, for forces, etc., nothing changes. Now, you could say, well, I'm sure I could come up with some experiment that could do that. That would be cool. But this theory assumes that that's not the case, that there is literally no experiment you can do that would tell you whether you're inside a box that's still versus inside a box that's moving at a constant speed forever and ever. That is a weird assumption, but it is an assumption you can make. So what that means is there is no privilege in this. Both of these reference frames where we're shining the light and watching this person move, and where this person is staying still and having the light go by, those are equally valid perspectives. And the second assumption is that in both people's perspectives, light is moving at the same speed. Now, those two statements together seem like they will create contradictions. They don't, in fact, but it creates very strange implications. Implications that are very counterintuitive and can't be easily demonstrated, but it turns out if you make these two assumptions, you get a bunch of predictions that you can confirm. Well, maybe you can't confirm, but that can be confirmed. The most fundamental of these predictions, for me, is that if this is true, if there is no preference between these two perspectives and that light travels the same speed from both perspectives, different observers, us versus this running guy, have different perspectives of how time goes by. That is a radical idea, but it emerges logically from the two assumptions. Let's think about how we can measure time. We can measure time a lot of different ways, with clocks, with various mechanical and electronic switches. But there's one way in particular we want to focus on here. It's a clock where the measure of time is based on how much time it takes light to go up and down between two mirrors. So somewhere you can hook this up to a clock. It's something that has a photo detector here, shine light up, light comes back down, that's a tick of the clock. And just however big you make L sets how long your clock ticks. Now, since light travels fast in practice, you can make this like a nanosecond, but we can imagine it being a millisecond or something like that. So this is a clock whose timekeeping ability is based on the speed of light. Now, you could say, but wait, I don't need to make a clock that depends on the speed of light. That's true. You can also make a normal clock, but you can set up a system where this clock and this clock keep the same time, okay? So that's a statement about the laws of physics. We can have a clock that keeps time with light, we can have clocks that keep time with other ways, and we can make sure they keep in sync with each other. So every time this clock ticks, the light goes back and forth once, okay? So fine, that's a weird kind of clock. Here's when things get fun. What happens if this kind of clock moves relative to you at a constant speed? So it's not just sitting here on your table, it's drifting by you at a constant speed. What happens then? Well, now the light still goes up and comes down, But now because the clock is moving, that light is moving horizontally as well as vertically. So it has to go along a diagonal line to get up to the top thing, and then has to follow another diagonal line to get down. So the light is emitted when the clock is here, it gets bounced when the clock is here, and it gets back down when the clock is over here. Okay, that should make sense. You shine the light, it goes up and comes back down on diagonal paths. Of course it does that. It's moving relative to you. But here's the thing. Light travels at a constant speed. So this light path is longer than this light path. This clock, even though it's got the same length between the mirrors, this light takes a longer time to make the journey. So even though this length and this length are the same, the time it takes for the clock to go, the light to go up and down is longer. So so in this clock, we've tuned it up so that a tick happens every nanosecond. That's not the case for this clock, even though it's identical to this clock, other than it moving. This clock, a tick, an up and down, will take more than a nanosecond. Now you might say again, that's a special case because it's a specific type of clock. But I can take this thing and have it next to another copy of this clock. These two clocks are in sync. The two clocks in motion also have to be in sync, or else in those clocks' reference frame, the laws of physics are different. It's not possible to sync up clocks that way. Something weird is going on. These clocks, these moving clocks, run slow. They take longer for a time step for things to happen. Now, given this is just geometry of how light travels, you can even say how much slower the clock is. And the book does this. I'm not going to expect you to memorize this formula, but it means that a time step of this clock, how long it takes before it goes boink, boink, is longer than the time step on this clock, which is sitting here in our reference frame. It's longer by a factor of the square root 1 minus v squared over c squared. Now, often, speed of light is really big, remember. So most objects, the speed is a very small fraction of this. So this is a really small number. And so this is basically 1. So the two times are almost the same. So we wouldn't notice this unless the speed gets up too close to the speed of light, which most of us don't do. Remember, that's very, very fast. So this isn't a big effect, but it says that this clock, specifically this style of clock, runs slow. But the key thing to note is we could sync a clock in our reference frame that worked like this with any other clock. We can do that with any other clock that's moving as well. This system could have been hidden inside another clock, or it could not be. Any measurement of time that is on a clock that's moving relative to you runs slow, because this could have been synced up to one of these light clocks. So in our reference frame, these two clocks keep the same time. In this reference frame, those two clocks should keep the same time. So not only would the light clock run slow, this clock will run slow. Anything that measures time runs slow. So if you were a person moving with this, and your perspective of time, like you're sitting there going 1, 2, 3, 4, 5. So if you're moving relative to us, the rate at which you call out those numbers is longer than you perceive, is longer to us than it is to you. Depending on your perspective, clocks seem to run slow. And this is symmetrical. This clock moving relative to us seems to run slow from our perspective. But if you were riding along with this clock, our clock would seem to run slow. This is really odd. And you could go like, wait, no, this can't possibly happen. It does. This is observable. Now, there's two different ways you can observe it. One is look at things moving at really high speeds, like subatomic particles. That's fine in there. Turns out the other place where this shows up a lot is GPS satellites. GPS satellites constantly communicate with things like your cell phone to tell it where it is, at least if you have a fancy one. Those satellites are well above us and moving often fairly quickly. And figuring out where they are relative to us involves timing everything carefully. If you don't account for this, what's called time dilation, this doesn't work. This is an observable thing that affects how GPS triangulation works. This is a real effect. And more recently, you can take a clock, a very precise clock, put it on a plane, fly it around the world, and bring it back. It will not have had as much time elapsed on it as an identical clock that sat by you the entire time. If you move a clock, it starts to run slow. This is bizarre, but it happens. And this is just the start of weird things that happen once you admit that these two assumptions might be right. The other one is a phenomenon that is called length contraction. It indicates that the size of objects depends on how you perceive them. This can be derived directly from our previous experiment. Say we have our happy clock here ticking away, and we have an object, a long bar moving by. And this clock has a paint sprayer on it. And when the clock ticks at, say, 0 milliseconds, and then again at 1 millisecond, it spits out a line. So as this thing came by, at 0 milliseconds, it sprayed this line, then the whole bar kept by, and then it sprayed another line. What's the distance between those two lines? Well, depends on how fast the bar is moving and how quickly the clock ticks. Well, if this thing was moving, for example, at 1 kilometer a second, and we put marks down every millisecond, then the distance between those spots is about a meter. Fine, that's straightforward. So this is what's happening from our perspective. But this bar is moving at a constant speed. It is sitting still in its own inertial reference frame. And in that frame, the clock is moving. So the clock puts down one line, then there's a tick of the clock, then it puts down another line. That's when those two events occurred. But this clock runs slow because the light travels further. Or if it's any clock, like I said, it doesn't matter. This clock is moving, though, to the left, or sorry, to the right, at the same speed as the rod was moving to the left. It takes more time for this thing to go through one tick, so it travels further along the rod before it makes the mark. So in this case, the clock is moving to the right at 1 kilometer a second, but it's running slow, so it takes more than 1 millisecond for the light to make the round trip. It actually takes something that depends on the square root of 1 minus v squared over c squared. So it takes longer. So the two lines are further apart in this reference frame than they are in this one. And that's not special again. For example, I could have arranged things to make it so that as this clock goes by, this thing marks the ends of the rod. So the rod's a length L that is exactly the right length to get one end marked here, one end marked here. That's a particular length. But now if we go back to the frame where the clock is stationary and the thing is moving, then it takes less time for that light to go up and down. These two things are still on the ends of the bar, but they're closer together. So this object is shorter than it used to be by that same square root of 1 minus v squared over c squared factor. Again, this factor is close to 1. So it's not noticeable unless you move at really high speeds. But it means that not only do moving objects have clocks that run slow, moving objects are actually spatially distorted. They appear shorter when they're moving than when they're stationary. This one's a little harder to demonstrate, but it does in fact happen. What this means is that how time and space are perceived depends on how things are moving. And there's various ways to make that sound elegant. I don't want to do them. I am saying that objects that are moving do appear to be shorter than they are when they're staying still, and that any clock that's moving, be that a light clock, be that a normal clock, be that the clocks that determine how a person perceives the passage of time, all of those clocks run more slowly if they're moving than if they're stationary. Now, if you are a clever person or just somebody who likes to argue, sounds like this sort of thing is just going to create paradoxes and contradictions where two things that just can't happen do. Like that events that clearly don't, that sequences of events or other things would lead to an explicit contradiction in how we treat the passage of time and space in these situations. And this is the basis of a lot of thought experiments or things that are really cool, like that are called things like the twin paradox or the pole in the barn paradox. These are cases where people went like, no, this makes no sense. Consider this thought experiment. It clearly produces a contradiction, so special relativity must be wrong. It doesn't. In fact, everything is consistent as long as you keep track of everything carefully. Usually it's a problem with matching our intuition with this very strange way to perceive the world. I would love to talk about these. If we had more time, I probably would. But these are paradoxes. If you're interested, please look them up and try and understand them, because they're places where you can go, oh, okay, what would actually happen in these situations? And can I understand how these can be logically reconciled? Again, I wish I could talk more about it. We just don't have time in this class. Okay, there is one other implication, though, I do have to mention. And this has to do with energy and momentum. These distortions in space and time that depend on how things are moving relative to each other propagate a lot of other basic quantities like velocity and acceleration. What this means is we have to be careful about how we define energy and momentum. Remember, The fundamental property of energy and momentum is that they are conserved quantities, that when we look at particular types of collisions, momentum is conserved, and under all situations, energy should be conserved. What makes these quantities useful is that they are conserved quantities. So you have to basically adjust your definitions of energy and momentum to make sure that's still the case. Now, and these are the generic expressions for momentum, which is a vector, and energy. Momentum is mass times velocity over 1 minus v squared over c squared, the same basic correction we had before. When the speed is low, close to the speed of light, this thing is close to 0, so this just becomes p equals mv. This is the standard expression for momentum. So this is a pretty reasonable generalization of what momentum ought to be in this very strange situation. The expression for energy, though, looks a little weirder. It's E equals mc squared 1 minus v squared over c squared. So the same correction factor is there, but this isn't obviously related to previously discussed concepts of energy. So we have to take a closer look at this. The thing to realize is that if v squared over c squared is small, then you can rewrite the square root expression in terms of a series of terms. And so in that limit where v is very small, you can rewrite this expression. It's approximately equal to mc squared plus 1/2 mv squared. That's kinetic energy. That's the energy we're used to. This is the thing that's, other forms of energy can turn into kinetic energy. Yay. That's the standard thing. That's the thing we normally get that we would be like the momentum case. But what's interesting here is there's this term, mc squared, E equals mc squared. You've heard that equation. This means even if the object isn't moving, even if its speed is 0, it has energy. And it has a lot of energy because c squared's a very high speed. Mc squared, that's a lot of energy. Wouldn't we have noticed that? Well, actually, no, because this is an energy that, as long as the mass stays the same, never changes. Remember, energy is something that can be converted. So you could turn potential energy into kinetic energy. If energy is, again, a conserved quantity, if the mass is constant, which for almost everything we consider it is, this thing never changes. So it's not an accessible form of energy most of the time. To access this energy, to turn this energy into energy of motion or potential energy or any other type of energy, you would need to change the mass of this object. And we haven't seen examples yet of how you can change the mass of an object. But that will be coming in the near future. As you know, this is the basis of nuclear power. And that involves both this stuff, which is relativity, but also the other big thing that came out from studying light, which was quantum mechanics, which will be the subject of the next couple of videos. Anyway, thank you for your time and have a nice day.